Welcome to Science for the People. I'm Rochelle Saunders. We're looking back at 2018 and calling out our favorite science news stories from this past year. The ones we think you should remember, or hear about for the first time if maybe you've been taking a break from the internet. And we've brought in a team of reporters from Science News to do it. This first story picks up from one of the top science news stories from 2017, proving that CRISPR continues to make big headlines. We've brought Tina Hessman-Saey back to talk about some more big CRISPR news. And if you don't know what CRISPR is or how it works, we'll have some links to catch you up in the show notes. Tina, welcome back.
Thanks for having me back.
So, only a couple of weeks ago, there was some pretty big CRISPR news that came out. Tell us about it.
So this news broke rather unexpectedly that a scientist in China claims that he has created the first gene-edited babies. What he says he did was to use CRISPR to edit out a gene that HIV uses to get into cells. So these babies are supposedly resistant to getting HIV infection.
So he did this at the urging of the parents. He did this as a general bit of science where they kind of found people to come and participate. How did this all come about? Do we know?
So he did this under his own initiative. He recruited 8 families from HIV patients, and he told them that this was going to be part of an HIV vaccine trial. That's what it said on the forms that he used to inform them about what he would be doing and to get their permission to do these experiments. This is called an informed consent form. So he recruited these 8 families. 1 family dropped out, but 7 families continued on, and he created, we don't actually know how many embryos he created. He said that there were 34 embryos, so we don't know how many belong to each family. But in this family, there were 4 embryos created. 2 of them did not have edits. 2 of them did. And the parents decided to go ahead and have those embryos implanted, even though one of them had an edit it was called an off-target edit. So this is that the CRISPR cut in a place that you did not intend for it to cut. And he said that it was far away from other genes and it wouldn't have any effect on the little girl. And the other embryo had an edit within the gene that he was trying to hit, which is called the CCR5 gene. But the problem is that nobody knows whether that edit would actually make the baby resistant to HIV. But the parents apparently decided to go ahead and transplant that embryo anyway. So, there was a combination of, it was very much his idea to do this, but also the parents decided to go ahead with this at each step along the way. Although there's a lot of controversy about whether he really adequately informed them about the risks and the consequences, and whether they were really informed about the whole debate about whether this should happen or not. I mean, he just sort of took it upon himself to defy what an international body of scientists and ethicists had said in 2015, that we're not ready for this yet.
Okay, so there's a whole bunch of stuff here to unpack. So the first question I have is, are any of these babies actually born yet, or right now are they still yet to be born?
So 2 babies were born. There is one apparently that may be on the way. Apparently a woman is pregnant, but It's in the early stages of the pregnancy yet, so we don't know if that baby will actually be born.
Okay, so now this was done, my understanding is this was done under the kind of guise, or the guise maybe makes it sound really kind of malevolent, but it was done to try and prevent the risk of the babies getting HIV. So is that a major concern generally I'm assuming that one of the parents would have had HIV, which is why there was potentially an elevated risk for the babies to actually get HIV?
Right. So these babies' father has HIV and their mother does not. So these babies were created through in vitro fertilization, where the father, first of all, although he has HIV, there are no detectable viruses in his blood. So his chance of passing that on are very low. And then when they do the in vitro fertilization, they actually wash the sperm to try and get rid of any remaining HIV virus that might be there. And then the scientists take an individual sperm that hopefully does not have a virus clinging to it and inject it into the embryo. Now, scientists say that since the mother does not have HIV, there's almost zero chance of the babies having gotten HIV from their father. And there's very little chance of them getting it from him after they're born, because HIV is just not casually transmitted amongst family members. So there's very little reason to think that these babies would be at any higher risk than anybody else of contracting HIV. But the scientists said that in the developing world, there's a lot of discrimination against people who have HIV. And the fact that these babies have a father who is HIV positive might make them more likely to be discriminated against in the future. But so I guess if you could say, well, yeah, my dad had HIV, but I was gene edited, so I can't get it, then maybe you would be free from discrimination. But then I would think that, right away there, how would people know that you had been gene edited, especially when they're trying to protect the privacy of these babies so that they won't spend their entire lives in the spotlight.
So one of the big controversies around this story about this reveal is that the justification for doing the science for gene editing these babies is not suitable based on the risk that they had for getting HIV. So it doesn't really have any good preventative value. And conversely, what we're looking at is potentially introducing risk to these babies by doing gene editing to them that we're not 100% sure how that will impact them, or whether or not it will have adverse impacts for them as they grow up. And that's one of the major points of controversy around this story. Am I correct?
That's right. So not only would these girls not be necessarily completely immune to HIV, because in the one girl's case, she has an edit that we really don't know whether that would make her resistant to HIV. But also, knocking out this particular gene only gives you immunity to the most common type of HIV. There are less common types of HIV that use a different protein to get into cells. So these girls would not be immune to those types of HIV. So there's not really necessarily a great benefit to these babies. But because CRISPR has been known to sometimes cut in places where nobody wants it to cut, you open up these children to having these mutations and rearrangements in their genome that they would not otherwise have had, and those might have disastrous health consequences down the line. You could be disrupting a gene that would lead to cancer, or even if it's not directly affecting a gene, you could be affecting parts of DNA that are responsible for turning genes on and off. And you could be affecting multiple genes in that way. And we just don't really know whether these babies really are free from those what are called off-target effects or not, because nobody has actually gotten a really good look at the data. The scientists presented it at an international summit on Wednesday, but nobody has really seen the actual data, just a few slides that he showed.
Tina, this is a fascinating development in the CRISPR saga, and one that has only just happened, so it's just made the cutoff into our 2018 top science stories of the year. And at this rate, I strongly suspect that you and I might be talking for next year's episode of our top science stories. For 2019, I look forward very much to hearing what's up with CRISPR this time next year.
It's a date, Rochelle.
If you want to learn more about CRISPR or the news about the first potential CRISPR babies, check out the links in the show notes on our website, scienceforthepeople.ca. Next up, Bethany investigates whether or not we found water on Mars.
Hi everyone, Bethany Brookshire here, writer at Science News and Society for Science and the Public. It seems like every year there's a new announcement about water on Mars. Is there water on Mars? Isn't there water on Mars? Does this mean there are aliens? Does this mean there aren't aliens? I mean, let's be clear, we're all in it for the aliens, so I hope there are aliens. But one of the biggest stories this year isn't that there's just water on Mars. There's a lake on Mars. A whole lake near one of the poles. Or maybe there's a lake, because maybe there's not. But to talk us through this polar pool is Lisa Grossman, the space writer at Science News magazine. Welcome, Lisa.
Hi, happy to be here.
First, I feel like I've been hearing about water on Mars for years. How long have we been finding evidence about water on the red planet?
Oh, for a long time. I don't know when the very first suggestion that there might have been water on Mars was, but one of the first times that they really felt like they had confirmed that Mars used to have lots of water was with the Opportunity rover. When it landed in 2004, it found these little hematite spheres they called them blueberries because they popped out of the rocks like blueberries popping out of a muffin. And those spheres could only have been produced in a wet habitat. So that was one of the first times that we were like, oh, there totally was water in like large amounts on Mars in the past. So most of the discoveries of water on Mars are about Mars's previous warm, wet, much more Earth-like history. More recently, there have been a couple of different suggestions that there's water on Mars currently. Like we've seen from orbit, we've seen signs of hydrated minerals. So basically rocks that have water kind of tied up in them, which also would have been produced in a wet habitat in the past. And there have been some controversial signs of like streaks of possibly salty water, but possibly nothing. Possibly like dull, dry avalanches rather than salty water in crater walls. And then like there's not a lot of water on the surface of Mars today. There could be water. There's water in the atmosphere, which could be kind of condensing in certain spots on the surface. And so that could indicate maybe there's some way for some really salt-loving, aridity-tolerant microbes to get a toehold. But it's not like it was, and it's not like it is on Earth.
So when you say there's water in the atmosphere of Mars, are there like, is it clouds? Or is it not that much?
Yeah, there are clouds on Mars. There are clouds of water ice, and some of the rovers have seen pictures. We have pictures from the rovers of them. They're very wispy, and they're not like big thunderstorm kind of clouds. It doesn't rain on Mars, but there is enough water ice crystals in the atmosphere to make clouds.
Wow, I never realized that.
Yeah, it's cool.
So tell me a little bit about this new-ish lake. Where is it? How big is it? What's in it?
Yeah, so this lake is at the South Pole, near Mars's South Pole, underneath an ice cap that is mostly carbon dioxide ice. It's about 1.5 kilometers deep in the ice, and it's pretty big. It's so depending on how deep it is, the lake looks like it's wide enough that it could have 10 billion liters of liquid water. So this is a huge amount of water as compared to the little droplets and streaks that we may have seen before. And it also suggests that if it's there today, it must have been there for a long time. And that is a good thing for if there is anything living there, that it has a stable environment to hang out in for possibly billions of years.
But you mentioned it's under this ice cap of like carbon dioxide ice. How thick is that ice cap? Is it under like just a thin shell of ice, or is it really buried?
It's how thick is the ice cap at the site of the lake or overall?
At the site of the lake in general.
It's a kilometer and a half. So it is pretty deep in there, and it's really, really cold down there. So that's one of the things that is potentially iffy about this discovery, is that they don't have a good way we don't really understand how water could remain liquid when it's that cold.
Yeah, because carbon dioxide ice is what, like -60? Is that right? It's really cold stuff.
Yeah, -60 Celsius is what we think the temperature at the bottom of that ice, like around where the lake would be. I think the temperature varies from the surface to the bottom, but yeah.
And it's under this gigantic 1.5 kilometers of ice. How did scientists find it in the first place?
So they found it using a radar instrument on a Mars orbiter. And this orbiter it's been circling Mars since 2003. It's on the European Space Agency's Mars Express spacecraft. This was one of the things that they have wanted to do with Mars Express since it got to Mars. And it just turns out that the measurement was really, really difficult. But one of the way that they do it is they bounce radar waves off of the surface. And we do this on Earth too. There have been lakes in Antarctica that were discovered the same way. So the idea is that the radar waves can travel through material as long as it's consistently the same kind of material. But when it hits a boundary between one type of material and something else of a different density, it bounces back. So you can see the reflection of the radar. And the brightness of that reflection changes depending on what the material doing the reflecting is. So the brightness of the radar echo from the interface between ice and rock is a different brightness than between ice and water. And water would be much brighter. So water is more reflective than rock. So in mapping the south polar ice cap of Mars and looking for bright reflections, this team, they had to do a special clever thing where they stacked many, many images on top of each other to get a strong enough reflection to see anything. But they found this little triangle-shaped region with an extremely bright reflection. And they ruled out a bunch of other possible things that they thought it might be. And the only explanation that they think is left is that there's a pocket of liquid water down there.
And you mentioned that it's really cold. It's like -67 degrees Celsius. How is it possible that the water could still be a liquid down there? I mean, salt can keep things pretty liquid, but salt has its limits.
Yeah, so one way is that there could be just lots and lots and lots of salts dissolved in there. It could be more of a brackish, mucky brine than just like water. It's definitely not drinking water. It's not like your tap water. And there have been some of the things that I was talking about before with the streaks in the crater walls. The salts there would be the kinds of salts that they thought they saw in those streaks are really, really good at melting water. So, if you sprinkle salt on your driveway to melt the ice in the winter, this kind of salt, it's a particular kind of salt called a perchlorate, could melt your driveway even if it were -50, -60 Celsius outside, which is roughly what it is here. So if those salts are present on Mars, and if you could get them in high enough concentrations in this lake that it could keep stuff melted for billions of years, then that could explain it. There have been questions about the accuracy of those measurements. Those salts might not actually be there in the same kinds of concentrations that we thought. So that way might not work. And in trying to figure out if the lake is even really there at all, there's another orbiter. There's a NASA orbiter circling Mars that has been circling Mars for a while now too, called the Mars Reconnaissance Orbiter. It also has a radar that looks in a shorter wavelength than the Mars Express radar. It does not see this lake. So that's kind of puzzling, that why would you see it with one orbiter and not the other one?
Could it be an artifact, or could it be a difference in what the wavelengths can detect? Yeah,
so that's one of the solutions that people have put forward for this, is that because they look in different wavelengths, maybe one of them just isn't getting deep enough. Maybe the shorter wavelength radar can't see all the way down through that 1.5 kilometers of ice and get to the point where there is a lake there.
Lisa, thank you so much. And I will be calling you again if we finally find aliens. So just so you know.
Please do.
We've got more information from Lisa about the water on Mars available at our website. So check it out. And next up, a kilogram is a kilogram, right? Well, not anymore. Sorry about that. Stay tuned.
Rochelle here again. This next story is quite possibly the one I'm personally most fascinated by, and admit I've been following for a while. It has to do with weights and measures and how we define them. Joining me is Emily Conover, physics reporter at Science News, to catch us up on the 2018 decision that is redefining the kilogram, literally. Emily, welcome to Science for the People.
Thanks for having me.
Okay, so before we can talk about the new definition of the kilogram, what was the previous definition of the kilogram?
It was based on this hunk of metal, a cylinder that was kept in a vault in France, and that cylinder was exactly 1 kilogram with no error on that mass.
So when we say exactly, how precise were we able to get that? Because obviously you need a really good scale to get that kind of precision that I'm assuming we wanted.
Yeah, so actually the kilogram is always 1 kilogram. You don't need to measure its mass to determine that it's 1 kilogram. It's what defined what 1 kilogram was. Then in order to find out what other masses weigh, you have to compare them to that kilogram. And that's sort of where the error comes in. When you measure any other mass, you of course can't do that perfectly. So that was kind of the funny part about it. And the weird thing is that if the kilogram were to change somehow, if you were to drop it and scratch it, then the mass of a kilogram would change slightly everywhere around the world instantaneously.
Okay, interesting. So you're telling me that if I donned a cat burglar outfit and snuck in to where this kilogram is stored and shaved off a little bit of it, would we basically have an entirely new kilogram that everyone around the world who uses kilograms would have to adopt to?
Mm-hmm. That was sort of the way that the system worked before, and that was one of the reasons they wanted to change it.
Right. That screams to me that that's highly problematic. I mean, obviously, it's kind of fanciful to say that someone would come in and change it or that it might drop. I'm assuming they treat it very carefully. But when we're talking about objects, they're not permanent. They kind of lose tiny bits and pieces of itself all the time just by existing in the world, right?
Right. Yeah. Or, gunk can collect on the surface. You can have chemical reactions going on. So for sure, it was not stable. And in addition to the kilogram, there's other copies of the kilogram. And those were occasionally compared to the original kilogram. And you could see that there were slight changes in the relative masses of those objects. So it's clear that it was not a constant number. And that's why now in this new system that scientists are adopting, they're using these fundamental constants of nature to define things like the kilogram, because these are supposed to be constant for all time, everywhere in the universe.
So when we're talking about making these metrics constant, the idea of the kilogram is actually one of the last, if not the last, of the sort of official weights and measures that has been pinned to something more sort of stable, right? Like I think we've done all the rest of them. We've pinned it to some kind of universal constant.
Yeah, so there were a few. So the kilogram is the last one that was pinned to a physical object. It was not the last. So there were a few that were not pinned to constants, but those were, say, defined in ways that were difficult to measure. So, for example, the ampere, which is the unit of electric charge, was defined by, take some 2 wires that are infinitely long and infinitely thin, and, some force, measure the force between them, and this is how you would determine what an ampere was. And that's not something you can physically create. So in addition to changing the definition of the kilogram, we've also changed, in this new change that was just adopted, we've changed the kilogram, the ampere, the Kelvin, which is temperature, and the mole, the unit of the amount of substance. So those were all being changed to rely on fundamental constants of nature in this update.
I'm sorry, did you say the mole?
Yeah.
What is that again? The unit for amount of substance? I have not heard of this one before. Please do tell.
Yeah. So if you've heard about, in chemistry class, you might have talked about, when you do a chemical reaction, you have 1 mole of hydrogen and 1 mole of, whatever else. It tells you sort of the amount of atoms that you are dealing with. If you've heard of Avogadro's constant, those are closely related. It basically lets you go from a atomic mass to like some number of grams of substance.
Interesting.
So that's also been redefined.
I had not heard of that one before. I am already even more fascinated. So, speaking of the kilogram, what is the new definition? If we've pinned it to some sort of constant, so we're no longer using a hunk of metal, we're going to use something that doesn't decay, that doesn't sort of have the potential to be dropped. What's the new definition?
So it's now defined based on a constant that's known as Planck's constant. And this is an important constant in quantum mechanics. And like I said, we believe that it's the same everywhere in the universe and at all times in the universe. And this is a number that shows up in all kinds of, quantum mechanical calculations and formulas, and it relates the energy of light to its frequency and things like that.
So how long has it taken us to figure out how to redefine the kilogram away from a physical object and towards something like pinning it to the Planck constant?
I mean, so part of it is the requirement that we understand quantum mechanics in order to make this. I mean, so we're basing this on a quantum mechanical constant. And that is something that we didn't understand, for much of the history of science. We didn't know what quantum mechanics was and how it worked and how to deal with quantum mechanical particles. So I think that might be part of it, that now we just have the techniques needed to define the kilogram according to Planck's constant. If you look at previous redefinitions of units that we've made, the meter used to be defined by the length of a bar, and then we redefined it based on the speed of light. So it's, now the meter is defined as the distance that it takes light to travel. The light travels in a certain amount of time. And that that was something that required us to be able to understand what the speed of light was and understand that it was constant. And that was, when we made that step in physics, understanding that the speed of light is a constant, that allowed us to redefine the meter. So it's kind of like, as we are understanding the physical world better, we're getting to a state where we can define our units based on these constant properties of the universe.
So now that we're changing the definition, are there things that are going to be easier to do with a more precise measurement that's a bit more reliable? I think in an article I read, it might have been yours, it called out potentially that this definition makes it easier to measure things that are quite a bit smaller than a kilogram. Is that correct?
Mm-hmm. Yeah, that's definitely one of the things that's going to get easier. It'll also be easier to make measurements from anywhere in the world. You don't have to have access to the kilogram to know what a kilogram is anymore, because Planck's constant is everywhere. You just have to have an apparatus that can, you can use to measure you can use Planck's constant to measure a kilogram with. And so measuring very small masses, you no longer have to say what fraction of a kilogram is a microgram, for example, which, doing that, sort of slicing up a kilogram in lots of tiny pieces to figure out what a microgram is something that added a lot of uncertainty to measurements before. And so now you don't necessarily have to compare to a full kilogram. You could say, okay, I'm going to use Planck's constant to determine what a microgram is, and then I'm going to say how many micrograms is this tiny thing that I'm measuring. So that's definitely one thing that's going to change. Although I should note, for most people, it will make no difference. They've very carefully organized this to make it so that the normal person is completely unaware and is not at all affected by this change. But people who make very precise measurements in industries like the pharmaceutical industry, it might matter to them.
Right. So I'm not going to have to take my kitchen scale into anyone for like a recalibration. It's not kind of fundamentally changed my life experience as it relates to kilograms.
Yeah.
Emily, thank you so much. I love the history around the official weights and measures and how we've been changing the definitions. It's something that I just really like thinking about. The idea that a kilogram is a piece of metal somewhere under 3 glass bell jars. I love that idea. And I will continue to love it even after we redefine the kilogram.
Yeah, it's a really fun thing to learn about, and the scientists who do this work are surprisingly interesting. Some of them got the Planck constant tattooed on their arms in response to this change, and that was really fun to talk to them about that.
Excellent. I will track down a photo of that and make sure that we link to it in the show notes. Emily, thank you so much for your time today. It's a fascinating story, and I'm really excited to read more about it.
Great. Thanks for having me.
We've got links to read more about redefining the kilogram and some of the other measures in the episode notes at scienceforthepeople.ca. Now, let's throw the baton back over to Bethany and a slightly more depressing but far more important piece of science news.
Bethany here. I'm back, and I want to talk about something lovely and cheerful and joyous this holiday season. You know, like how climate change is going to kill us all. In fact, it might already be doing it. Happy New Year, everybody! Here to talk us through the hot topic is Carolyn Gramling, the Earth and Climate writer at Science News Magazine. Welcome, Carolyn.
Thanks. Happy holidays, everyone.
Climate change is killing us all.
Climate change.
So how much, I wanted to start with kind of the basics. We know the climate is changing. How much has the Earth warmed so far compared to what? How quickly has this happened that we are calling this global warming?
So, the usual metric is pre-industrial times, before we started emitting large volumes of fossil fuels into the atmosphere. So compared with pre-industrial times, global average temperatures have increased by about 1 degree Celsius.
And to be completely basic, what's causing it?
Well, it's essentially the emission of fossil fuels into the atmosphere. So primarily carbon dioxide, but there's also other greenhouse gases such as methane that are up there and are creating this effect where radiative heat bounces back to the surface of Earth rather than radiating back out into space.
So we've got a nice warm blanket of our own carbon dioxide emissions
exactly.
smothering us slowly to death.
Smothering us slowly, yes.
And I know that the Paris Climate Accords had a lot of countries agree to keep warming to below 2 degrees Celsius. Why did they pick that 2 degrees Celsius mark?
Well, at the time, people thought that 2 degrees Celsius was a very, very conservative target, and a target that would prevent large-scale environmental changes from occurring. So this is, 2 degrees Celsius by the end of this century, so by 2100. But even at that meeting, which was at the very end of 2015, there were a lot of island nations and some of the other countries that will be most severely impacted by future changing climate who were concerned that 2 degrees itself was not strong enough, and were actually advocating for an even more stringent target of 1.5 degrees warming by the end of the century.
And why did they think that 2 degrees was not stringent enough?
Well, there was a growing body of literature, although in the last few years since that meeting, it's actually blossomed. But even at the time, there were some studies that were suggesting that the planet was warming faster than we had anticipated, and that the effects that we would start to see from 2 degrees were actually more than we thought they were going to be. So in terms of sea level rise, in terms of impacts on biodiversity, in terms of, melting ice sheets of Greenland and Antarctica. But there wasn't very much data yet on that. And that was something that people noted at a UN meeting in December 2015. They noted that we needed more information to really know if there would be a big difference.
And now people are talking about 1.5 degrees Celsius as a better target instead of 2 degrees Celsius. Why is that considered to be a better target?
So what has happened in the last couple of years since that meeting is that scientists have really come through, and they have produced hundreds of studies just in those 2 years to try and figure out exactly how will things be different, how will the world look in a 1.5 degree warmer world versus a 2 degree warmer world. And they have all found that there will be significant differences, whether you're talking about, habitat loss, whether you're talking about sea level rise, or whether you're talking about ice sheet loss. 1.5 degrees is a far less devastating target than 2 degrees even.
And what would we have to do? I know originally 2 degrees, it was kind of a compromise because it's hard to keep warming down, right? What would have to happen to keep warming below 2 degrees Celsius?
Well, most scientists at this point, and this came out in the IPCC report that came out in October, we are most likely going to surpass 1.5 degrees of warming by the middle of this century. So to get down to, just 1.5 degrees by the end of the century, that means we actually have to remove carbon dioxide from the atmosphere that has already been emitted. And that's especially tricky because we're still emitting fossil fuels. We're not going to actually suddenly stop on a dime. And not all nations, including the U.S., have even signed on. So that is a tricky thing. And the only way that we're going to get there is by drawing down these gases from the atmosphere. And that gets us into a whole new area of technology research called negative emissions technologies.
So we were talking about 2 degrees and we were talking about 1.5 degrees. Mm-hmm. For 2 degrees, could you just get away with stopping carbon emissions?
Maybe. Yeah. I mean, we still might need to have these negative emissions technologies. It really depends on at what rate we continue to emit now. And so much is dependent on what happens in the next decade. If we start changing our fossil fuel emissions, and also if we start, changing how we live our lives in terms of, that kind of consumption, I think we can make great strides towards that. It might be that we will still need to pull CO2 out of the atmosphere just to get to the 2 degree target, let alone 1.5.
And you're talking about pulling carbon out of the atmosphere with these negative emission technologies. Mm-hmm. This sounds very complicated.
Some of them are and some aren't. Reforestation, planting forests to pull the CO2 out of the atmosphere, that is one technology that is already in use. But the difficulty with that is that in order to plant forests that are big enough to really have an impact on the CO2 already in the atmosphere, you would get into a whole land use issue. Land is going to be a valuable commodity, and using it for this means you're taking it away from other purposes, for example, producing food crops. So that area is fraught. But there's other kinds of technology that the technology is already proven, but haven't been scaled up to the commercial scale, such as direct air capture, where you're actually pulling the CO2 out of the atmosphere. That's been demonstrated, for example, by Norway in offshore platforms, but it has not yet been scaled up to commercial scale.
And we're also talking about reducing our own emissions. This is not just like, turn off the lights when you leave the room.
Right. So there are a lot of things that individuals can do. There's been a lot of discussion over this past year, for example, about eating less red meat. Cattle farms are known and have been shown to take a great amount of resources. So eating less red meat would be one way that people can change their activities, using more energy efficient appliances, traveling less, particularly by air. These are all changes that people can make in order to reduce their own carbon footprint.
Well, Carolyn, thank you so much for making this incredibly depressing topic so much more real to us. And if you want to hear even more from Carolyn, well, you are in luck, because next up, Rochelle will be talking to her about another big story of the year, a giant freaking crater. At least it's not climate change. Stay tuned.
Hello, Rochelle here again. Several weeks back, we discovered something interesting under the ice of Greenland, a 31-kilometer-wide crater. With me is Carolyn Gramling, Earth and climate writer at Science News, here to talk us through it.
Hi, thanks for having me.
So start maybe by giving us the rundown. What exactly did we find?
Well, they found a bowl-shaped depression under the ice of Greenland, and it's almost, I don't know how to say, almost certainly a crater, but it's very, very likely to be a crater that was formed by an impact from some extraplanetary object. And the way that they found this was kind of serendipitous. They were actually, so NASA has programs that have been scanning Greenland's ice to study ice mass loss over the years. And every year they go up there and they look at the ice with airborne radar. and this group of scientists just happened to see this round shape, and they were like, that looks kind of interesting. And they thought, what if we hire a plane of our own with ice penetrating radar to go back and take a closer look? And they did. And they think that they found a crater.
Okay, so what do we mean when we say it's underground? I mean, how do we know it's there if there's stuff on top of it?
So it's not underground; it's under ice. There's a whole lot of ice from the ice sheet that sits on top of Greenland that is also sitting on top of this crater, and this ice penetrating radar, actually, the ice is fairly transparent to it. And so they can see right down into the bottom. It sends out these pings, and they ping off of different things within the ice that reflect the signal back. And the strongest reflector is the ground itself. So they can they get little pings back from different layers of ice that have collected over the years from, snow, fall, and so forth. But then they get a really big ping back from the ground. So that's how they basically know roughly where the ground is, how deep it is under the ice.
So remind me again, how much ice are we talking about here that they're sort of going through to find the crater underneath?
It's about 1 kilometer of ice.
Oh, okay. So a serious amount of ice.
Yes. Yes, a big, thick ice sheet, yes.
So when did we find this?
Well, they actually think that they spotted it in about 2015. So NASA's IceBridge mission was doing its scans, and they captured this image, and the scientists were just looking at it back in 2015, and that's when they thought they saw it. And then they sent a plane back the next year to take some more pictures or images with radar. But yeah, it's been 3 years that they've kept a lid on this thing. And they didn't want to talk about it for all this time. So they're very excited to finally have it out there.
Interesting. So this was a stealthy secret, and then its presence was announced to the world.
Yes.
So
I would say that they were very relieved when they talked to me. They sounded very relieved to not have to keep it a secret anymore.
So do we have any idea how old this crater is?
Well, that is sort of the question, is how old is this crater? And they have a guess based on the ice that they image the ice using the radar within the bowl-shaped depression. That is probably a crater. And they can see the ice that looks very clean and sort of, linear layers that have been deposited year after year of snow and ice, going back about 11,700 years. And that would be the beginning of the Holocene, the modern era. And then layers that are below that are very jumbled up. And so it's very hard to say what happened before that. And based on some other features, including what they call cross-cutting relationships. So there's streams that were beneath the depression. They think it probably is younger than about 2.6 million years. So it's somewhere between 2.6 million and 11,700 years old. But within that, they don't know more.
That seems like a big region of error.
That is a huge region of error, yes. And, there are some scientists who are skeptical that it's, even younger than 2.6 million years. It's very rare to have these kinds of impacts, really, especially one that would be as large as this. So they're highly skeptical, even that might be the age.
So is the complexity around dating this crater because it's buried under a bunch of ice? Like if that ice wasn't there, if we could actually get to it, would it be easier to date, or is dating craters just a tricky thing, full stop?
It would definitely be easier to date. They can be tricky. Chicxulub, one of the things that's tricky about that is that it's underwater. And so, yes, the idea that this one is on land is very exciting, but it is under all that ice, and that is the thing that's tricky. So if they really want to get out there and date it, I think the team is hoping that they would be able to drill through the ice and down into the ground itself. But that is expensive, and it's very hard to get to this place. So it's it's a challenge logistically.
Yeah, I'm looking at the photo that is in one of the articles on Science News that you wrote, and looking at where this crater is, it is definitely in a non-accessible place. It's
helicopter accessible only.
Yeah, it's quite far north. It's sort of on the far northwesterly part, I guess it would be, of Greenland.
Yeah. So I'm not even sure how they would bring in all the equipment. Yeah, it's tricky. As it was, they had a very small window of time because they came in with a helicopter, and they were scrabbling around in the earth in the ground right outside the ice margin to see if they could collect samples to see what sort of chemical composition is in those sediments right outside the ice margin. But that's all that they could do on that trip. So it's a mystery.
So one of the other interesting things about this crater is that, or the suspected crater, I suppose, is that some people are saying that it might be tied to a 1,000-year-old cold snap known as the Younger Dryas. Did I pronounce that correctly?
Yes, you did. Yes.
So before we get into why this might be connected, what is the Younger Dryas?
So yes, it's this cold snap that happened between about 12,800 years ago and the start of the Holocene at 11,700 years ago. So it lasted about 1,000 years, and the planet got very suddenly cold. The northern hemisphere in particular got very cold all of a sudden. And this was part of, in the middle of this like long-term warming up after the last glacial maximum, which ended around, 20,000, 18,000 years ago. The planet had been warming up, then all of a sudden it got cold for 1,000 years, and then it continued getting warmer to today. So it's mysterious. We don't really know why that happened. There are a lot of theories for that. But there's this one group of scientists that has been pushing this one idea for the last decade, that the thing that kicked that off was some sort of an impact. And they have a very, I don't know how to put it, sort of a unifying theory for like a whole bunch of things that they say happened at that time that were all started because of this impact.
So this is a fairly controversial hypothesis. This is definitely one that doesn't have any kind of consensus built around it, correct?
Yes. I mean, I would say that it's, most scientists do not think that this is what happened. It's this one group of scientists. They're all sort of from different fields, it's very interdisciplinary, but they've all been publishing papers, over the last decade, finding different ways to try and, support this one hypothesis. And so, of course, the big question now that this crater has been found is this the smoking gun, right? Is this the crater that these folks were looking for to, as a demonstration that their hypothesis is real? And as I say in my year-end story, I wouldn't get too excited about that just yet.
So, setting aside this particular hypothesis, looking at the size of this crater, what kind of impact are we talking about? When we say 31-kilometer wide crater, I mean, I have a very difficult time understanding, is that big for a crater? Is that medium size for a crater? Where does that sit on our scale of Earth craters?
It's pretty big for a crater. Yeah, it would be in the top 25 of the ones that we know on Earth right now.
So they're definitely,
it's pretty big.
I'm assuming then there definitely would have been, whenever it hit, whether it meets with this timeline for the Younger Dryas or whether it's in one of, somewhere else in the 2 million year error bar, it would have definitely caused some major impacts, both physical impacts and also general impacts around the globe. What kinds of impacts would we be talking about from an impact of this size?
I mean, I think there's little question that it would cause major environmental impact for sure. Climate impacts, that sort of thing. One of the things about the Younger Dryas impact hypothesis is that they think it was specifically fragments of a comet, and that some of those fragments exploded in the atmosphere, and those explosions, called airbursts, produced widespread wildfires across North America. And so that is not necessarily, depending on what hit the planet and formed that Greenland crater, that may or may not have produced wildfires. They are certain that it was these comet fragments, but the researchers who found the crater don't think it was a comet fragment.
How do we know if it was a comet fragment or something else?
So that's where the geochemical data would come in, and that would, they would love to go back and collect more to try and really get a firmer picture. But what they did find was they collected some data from what they call the glacial outwash, which is these streams flowing out from beneath the glacier itself, meltwater that's just flowing out and collecting right outside the ice margin. They collected sediment there. And they found elevated levels of platinum and copper and gold and similar platinum group elements. And the ratios of those elements to one another can tell you a lot about what that impactor might have been. And so they think, based on those ratios, that it was most likely what we call an iron meteorite, which is, it's the remnant of the core of an early planet or an asteroid. So just like Earth's core, very heavy and dense. Whereas a comet would have a very different geochemical composition.
Comets are there's quite a lot of ice in them, isn't there?
there's a lot of ice, and what sediment there is. They're like sort of balls of gas and dust, and the dust. There could be platinum there, but it would have a different sort of, the ratios of platinum to some of the other platinum group elements and other elements would be more like the, primordial stuff of the solar system, as opposed to this very differentiated, highly worked stuff that's been cooked by heat that you would find in these protocores.
Links to more info about the Greenland crater will be in the show notes. Last, but certainly not least, I throw it back over to Bethany one last time for a science story all about new neurons.
Hi everyone, Bethany again, and for our last big story of the year, I'm about to nerd out about neuroscience. And to do it, I am joined by my fellow nerd, Science News neuroscience writer Laura Sanders. Laura, thank you for being here.
Thanks for having me.
We are here today to deal with what is becoming a kind of epic neuroscience debate. It's basically the brain science equivalent of a fistfight. And so, for this purpose, Laura and I are here with some drinks just to keep it interesting. Cheers, Laura.
Cheers.
All right, here we go. So, for a long time, scientists thought that once you became an adult, you had all the brain cells you would ever have. The idea was that babies grew tons of new neurons, but that process slowed down as we got older and stopped in adulthood. But in 1998, that wisdom actually was knocked down, right?
Yep, that's it.
And
there was this really interesting study that found traces of a chemical that can get into cells and track when they were born. And very surprisingly, they found these in the brain.
So they found that the brain was growing new baby neurons, even in adults. But how many new brain cells did we think adults generally grew?
Well, so that study was a little hard to tell, but a later study in 2013 was able to measure that. And the number is kind of shocking. They estimated about 700 new neurons every day to each hippocampus, which is this memory center in the brain.
That's a lot.
So yeah, you're talking 1,400 new cells every single day.
It was funny because when I was reading about this neurogenesis literature, so the birth of new neurons in the hippocampus is called neurogenesis, hippocampal neurogenesis. And I did a lot of reading on this in my postdoc where I studied hippocampal neurogenesis.
Mm-hmm, yeah.
And when I would read about it in humans, it always seemed like really very few. And in rats and in mice, when I was actually doing experiments, it really wasn't that many, but I think that's partially because of our processing techniques. But you mentioned they're in the hippocampus. What are they supposed to be doing there?
Well, that is the active research. So some people think they have big roles in things like memory and learning. Other people think that they are important for things like stroke recovery or, protecting against dementia. So yeah, it's kind of an open question, but in general, I would say people think they're doing good things, which is why this whiplash, this huge debate that sparked this year is so compelling and important to settle. We'd really like to know the answer.
Yeah, because what happened was this year at the Society for Neuroscience meeting, what went down?
Yeah, so it was actually last year's Society for Neuroscience meeting, a bombshell presentation, I would say, of a research group from UCSF that found absolutely no whiff of neurogenesis in adult human brains. So they presented it there. They then published their results in a pretty comprehensive paper early in the year, so in March of 2018.
And since then, there's actually been even more whiplash?
Yes. So, okay, that was March. April comes along and a different group publishes a stem cell paper saying, yes, not so fast. There is neurogenesis in the human adult brain. I could go on. Then in July, there was a cerebral cortex paper that again said, no, we're not finding it either. So at that point, you can imagine tons of people jumped in, lots of experts who have been studying this for a very long time wrote a pretty large number of commentaries and perspective pieces and arguments about which group is in the wrong and which group should be more, careful with your methods, or here's why you're wrong, here's why we're right. It has turned into a huge debate.
And why is it important that we know whether or not humans produce new neurons?
Yeah, well, for the reasons we were talking about just a little bit ago, if they do have roles in things like memory and learning, if they're protective in some way against dementia, if they're sources of kind of brain renewal that you can then harness in some therapeutic way, that would be a really big deal. And then to find out, if it doesn't exist at all, I think it would. I don't know. You tell me, how would you feel as a hippocampus neurogenesis researcher?
I have to admit, I would be, I don't want to say devastated, but I'd definitely go to the bar, because I was studying hippocampal neurogenesis because I was looking for mechanisms of how antidepressants function in the brain. And in mice and rats, we know that in susceptible animals, which is not all animals, hashtag not all animals, if you give them antidepressants, after about 21 days, when you'd normally start to see therapeutic effects in people, in animals, you start to see therapeutic effects, and you also start to see the birth of new neurons in the brain, and that's associated with antidepressant effects. And so if that didn't happen in humans,
right,
I would feel very strange about all of my published papers.
Have a drink of wine.
And the taxpayer dollars that I spent, it would take way more than one glass of wine. But anyway, this is still controversial. We're still going back and forth. Why does this keep happening? Why do we not know whether we make new brain cells or not?
It's a really, really hard thing to see. In human brains, we have no good way to really look there. In animals, you have way more tools at your disposal. You can slice the brain up, you can put markers on it and put it under the microscope. You can do techniques that allow you to look in the living brain. You can kind of trace neurons as they're being born. In humans, we have none of that. So the way that these groups, this year anyway, have started looking are mostly post-mortem samples. So people who either donated their brains to science, or who underwent brain surgery and had some chunks taken out that they then donated to science. And then scientists apply certain markers, things that latch on to proteins in the cells that they think mark new cells, either newborns or you're relatively new in their life. Then they look under the microscope and count. And so when you're doing that kind of work, you have all sorts of confounding factors that can mess with what you see. So it matters how healthy the person was before they died. It matters whether they had a psychiatric disorder. It matters how long from their time of death to the time you're looking at their brain. There are all of these really finicky things that have to be just perfect to get the good view that you need. And then on top of that, people don't really agree on what the best markers are. So the proteins that mark certain cells are kind of controversial. And I think so people don't necessarily know what, the gold standard would be in that case.
Well, Laura, thank you so much. And I hope next year we can have you back and say, Eureka, we know the answer, whether or not that makes me happy. If you'd like to learn more about the new neuron fight or any of the other topics on this week's show, we've got links for you at scienceforthepeople.ca. While you're there, follow us on Facebook or Twitter. Give us a good review on iTunes so we reach more people. Maybe even support us on Patreon and give us access to awesome bonus content. Next week, we'll have a rebroadcast to give our editor a well-deserved holiday break, but we'll be back in the new year. So have a great rest of 2018, a lovely holiday if that's what you do, and a happy new year from Science for the People.
Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten and consulting support from Desiree Schell. Our frequently seen guest hosts are Marion Kilgour, Anika Hazra, and Jessica Yaros. Our theme song is called Binary Consequence, and it was written and recorded by Fractal Pattern. Science for the People is entirely listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount, or you can send us a one-time donation in any amount via the donate page of our website. Science for the People is created in partnership with the Skepchick Network, a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by science news writer Bethany Brookshire and me, Rochelle Saunders.